Okay, now essentially we have seen the role of the pseudo inverse in general linear algebra setting, and now I'm coming again to the Gabor setting. So in a nutshell, the question is, what is a Gabor frame? Well, it's a generate in finite dimensional setting. It's a setting, a collection of vectors, and these vectors are all of a certain, obtained by a certain procedure, namely starting from an individual Gabor window. Maybe I also recall this here. I would like to say we plot, and of course we plot our window in the centered way. And also, of course, we should first generate the function. And then we use a lattice. That means we have points. Maybe also show your lattice lambda. And SPI is the general command indicating where a matrix has non-zero terms. Now, my lattice point routine says, well, put in the first column at a distance, at the vertical distance, which is the frequency direction B, which is 16, you put 1. So in the first column, I put a 1 at position 1, because I have no zero component. 1 plus 16 is 17, 33, and so on. And once I've filled the first column at equidistant things, 16, of course, has to be a divisor of the signal length 480. And I'm not choosing a power of 2 because I would like to have, maybe that's another thing. What are possible divisors of my size n? There's a small command, actually, maybe a little bit looking behind the scenes. All diff or proper diff is this, and I can try to just type it. All diff, you see it's not consistent. And this was this very elegant, well, it's 2 half-line code was created by Norbert Keiblinger. So I'm not spelling it out by this, but roughly speaking, I mean, yeah, I can tell you what the code is doing. It says, well, you have the number n, so in our case, 480. And yeah, so maybe I'm showing you the, no, first I discussed it. And then you take this integer and you divide it by a vector. Now, of course, you cannot divide a number by a vector, but you can divide a constant vector by a vector of the same length. So the dot divide command tells you that you should take n as a constant vector of the length of the denominator, and there you divide by n minus 1, n minus 2, so decreasing order up to 2. So you take all possible divisors, which are the numbers from 2 to n minus 1. And then you are saying, where do you get an integer by this division? Because exactly when you have a divisor, you get you get a divisor. So you're saying where in these coordinates is a logic equality? Where is the d equal to the round d? So where is this division? An integer. And then the output is to say, well, wherever you have a 1 here, you're giving us these numbers. So if I do this again, all diff of n, not sure. Okay, so here, I don't know, maybe the workspace does not, yeah, maybe I should run this section at least, yeah. I will run this section. Then we will see the all diff here. You'll see clearly the number of divisors is much more rich. And now I would like to show if this works here. I mean, one of the reasons why people are using, that's my claim for CD player 44,100 is because this is a number which has extremely many divisors. It has 79 proper divisors, and it starts with divisors are 2 and 3 and 4 and 5 and 6 and 7, no 8, but 9, 10, no 11. So the larger prime numbers are not appearing, 11, 13, 17, and so on. But we have 9, so 3 squared. We have even 25, 5 squared. We have 49, 7 squared. And of course, we have 2 and 4. And that's actually what it is. So the factorization of this nice number from the point of view of CD player is 2 squared times 3 squared times 5 squared times 7 squared. So it's extremely rich in divisors. So for Gabor analysis, for large dimensions, that would be a good example because you have a lot of lattice constants. That means you have a lot of grids which you can use here. So now the spice command doesn't work properly. I'm not sure what's working out here. So there seems to be, yeah. I'm not clear, it's not clear to me why we get this strange figure. I will have to correct it, but I don't want to discuss it. And the second one is this discrete Gaussian. So you see it's roughly going from minus 240 to plus 240, and it's a very well localized function. Now, I will need later on some random signal because I want to show that we are able to synthesize this random signal using Gaussian functions. Gauss functions as a building block. Now, a Garber family with the parameters GAB, and I should say maybe we look at the number of lattice points that we have, and we look at the size of this Garber family. Maybe I'm putting a break here. So I'm only running this part of the, then you see, of course, every lattice point is generating a function. Now every lattice point, I'm not sure I will, maybe I'm, yeah, well, it's not meaningful. So normally you should see, maybe run this first part once more. Yeah. Maybe I should do a figure command to open a new figure. If it's not working, I will stop playing around. Yeah, this is a bit strange. Yeah. So you should see a lattice point indicating at the positions in the matrix. Yeah, maybe I'm just doing a spy command. Maybe that's working more properly. It's an unexpected change problem. It shows you the position in the 0, 1 matrix, which are describing the points where I have non-zero entries in the matrix. Okay, now it's not working for some strange reason. Okay, but I have 720 points. So this is how many ones I have in this 0, 1 matrix in this nicely organized way. And of course, you see the number of row vectors, and each of them is in our signal space 480. Now, the first observation that I want to convey to you is that if we want to look at, understand the pseudo inverse of a Gabor matrix, and clearly here we are in a situation that we have more vectors than the dimension. So we cannot get a full range here. And then you would take the pseudo inverse, and you see I'm taking the pseudo inverse of the Gab prime. I could take the pseudo inverse of Gab prime outside. And actually here there is no distinction between collections of row or column vectors. So this is the dual system. This is the system that you would use in order to get coefficients, which are the minimal norm coefficients because we have a redundant system. And then the first observation is this system a collection of, is this again a Gabor collection? And the answer is, from this experiment now, we just take the first row, which is corresponding here. And we, again, I'm showing you this picture, sorry. It's the Gabor dual window dual window for our AB situation. Sorry, I should plot in the AC command. And then we can take a look at this thing here. And once it pops up, yeah, and it's having a very typical scheme. Now, I was already indicating that we have many fast algorithms, and just let's say GAB DDD. It's a strange name of GAB. No, it's yeah, okay, it's GAG minus G dual AB. I'm not using the then and I only make a new section. If I only want to, okay. Yeah, I'm not completely sure. Maybe I did not load my collection of standard routines. Maybe this is the problem. No, I think the error is elsewhere. It's just here, of course. I was not computing the right thing. Yeah, you see, this is an algorithm which would be done by some conjugate gradient algorithm or so. But we also have other methods. So maybe we just say SGAB is the operator which describes the frame operator. And because we have a system of row vectors, we first take scalar products. So we take GAB prime with GAB. So just also size of S GAB to check that this is really an n by n matrix, 480 by 80. And for example, we could say, is this a good, are you a good matrix? And the answer will be, in our case, it's a very decent matrix. Condition number, which is never less than 1, is less than 2. And so it's a really positive, we can check it's a positive definite matrix. And so we could say, is it true that we can take the inverse of the Garber frame operator? Now we have to apply it from the right because we have systems of row vectors, and get the same thing as with the Garber dual AB. And there's another way to say, well, that's even more tricky. We divide from the right by AB. That's a more elegant to say we are solving an equation S candidate for dual Garber window equals the G. And we'll see that in both cases, we should get satisfactory answers. Yeah. So, yeah, of course, that's a stupid typo. So actually, you see that in this case, the result seems to be identical, but I'm not sure. Okay, so now the other thing is that the question is, well, if somebody has taken, has applied, no, if somebody is interested to do a Garber expansion. So again, recall the Garber system is hopefully a system which generates any signal. Then we hope that we can get for every signal the coefficients by applying the pseudo inverse. So essentially what I'm writing here is PINV of GAB minus GAB. And of course, the answer is, in this case, because it is a generating system, it has full rank. We could also say, look at the, yeah, there maybe we also added here, rank of GAB must of course be also the full rank. So we know every vector in this 480 dimensional space can be represented, but because of the redundancy, we have a lot of things. And then we know the pseudo inverse will be the solution of the minimal norm solution. Now, the next line is giving a statement that there is a symmetry. symmetry between the dual window and the other one. So the system is, so this is saying that both the dual system, which is the Garber system by this experiment above, by this line here, by this statement, the Garber system from this individual dual Garber window is allowing you to put it to the left or to the right, and you will get the identity matrix. Recall that in both of these cases, we are factorizing a n by n times redundancy matrix. So 720, I should also mention this. Maybe I should say that the redundancy factor is essentially n divided by a times b. You could better say it's the quotient of n over a times n over b divided by n. So it's the number of terms that we have compared to the dimension. So in our case, it would be 720. It should be 720 in the number of building blocks divided by 408 years. Okay, so we have this situation. And now, of course, I want to demonstrate that instead of really taking a full matrix and doing scalar products, so this is good for analysis to understand what we are doing, but for fast computation, we should use a command which is more elegant and more efficient, and that's the STFT command. So it's very natural to say, well, you want to see the short time Fourier transform or the spectrogram of some random signal, and with the window G, and you want to sample it and first the lattice constant for the time and the frequency. Later on, we will be able to see other lattices and so on, but that's the first thing. And the point is now of this experiment to see that this is exactly the same thing that you get. I mean, probably we have meanwhile another random function. No, it's already okay. Is that this is the set of scalar products. So if we are saying that this is the identity, then we're saying, well, somebody is giving us this information. So he has sampled the short time Fourier transform at the positions of the lattice point, and we would like to recover it, and we do synthesis with the dual window. The other, yeah, maybe I should also tell you, there's a command Gabor. So maybe I'm doing a random, maybe AB is, you're giving me some samples of a sampled short-time Fourier transform, and we know this would be, or maybe even complex valued random Cn of a matrix. In terms of height, we have n over b entries in each column and n over a in this. So this is a matrix. And we could say, well, you want to do Garber synthesis. XS1 is that somebody is saying, well, choose all these vectors. Now, that's interesting because we want to do it with the Garber family. So we have to do a right matrix multiplication with the Garber matrix. But you're giving me a matrix, so it's important that there's a consistency, which is, of course, taken care of. You don't have to learn it with the vectors, with the numbers, with the coefficients that we have in the correct order. And the correct order is, of course, reading it column-wise. So we have to convert this into a vector and then convert this column vector into a row vector. Now it's a row vector where all these coefficients are appearing in the right order. And I'm doing synthesis by doing linear combinations with this, or XXS2. I have a Garber synthesis command, and I'm saying, well, you give me the matrices, because if from this input I can already determine the lattice constants, because it's part of the format, I can also say I have to compare now the one way of really individually doing a linear combination with the other one with an elegant command. And so let's try to do this. Okay, sorry, typo. And we observe, hopefully, that, yeah, this is really the same. Actually, it was an interesting step by one of my former students that we had various of these tools already. And he was observing that in some sense, from a matrix point of view, analysis, taking short-term Fourier transform is matrix multiplication with Gab prime and synthesis with Gab. So he said, how can it be that we have an efficient code for the STFT and a not so efficient, much slower code, maybe like 3 times slower than this? And that's actually what was the motivation to try to get the faster code, which is now here in the Gaussian. We can also compare now random signal applied to the Garber frame operator, or the more efficient way would be, well, what is the Garber frame operator actually doing? Is taking the samples of the short-term Fourier transform at the lattice with lattice points A times B and synthesizing it with the B. And I will check, I have not done this, not prepared this, but okay, where's something? Okay, I have not chosen the right name. Probably I should just redo it. So I would say the Garber frame operator is the operator which is first taking coefficients with AB and then doing synthesis with AB. So maybe that was the reason why it didn't work properly. Yeah, but you see, this is doing a full matrix multiplication, which is great if you have small dimensions in order to understand the effects, to determine eigenvectors, eigenvalues, blah, 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 and so on. Now, the full short-time Fourier transform, maybe I should recall to you, maybe I'll leave it. If a short-time Fourier transform of a random signal would fill the full-time frequency plane, but if I compare, this is another kind of private NuHAG routine, comp STF means compare the short-time Fourier transform now meant in a continuous way, but of course with the center put to the middle, also with the image C command, and because it's a very small center in the middle, I'm zooming both of them. And if I zoom all the windows that I have opened here, I have just 2 windows, I'm using the do all command. So this is do all is a nice subroutine helping to do adjusting axis for a collection of plots and so on. So here it's just zooming at both of them, not just subplot 1 to 1, zoom 4, then go to subplot 1 to 2, split the screen into 1 direction vertically and 2 directions horizontally. That's why I'm saying subplot 1, 2, and then the running number, which is first one here, second one here. Okay, so you see what happens here. There is a little bit deformation here, and if you would look at it in the logarithmic scale, you will see that's a bit more spread out. And the fact is that the short-time Fourier transform and all these automatic things, you see I'm not saying which window I should use, is using the Gauss window of this size. So here it's the Gauss window, short-term Fourier transform with Gaussian window and Gauss as signal, and here the dual one. So this is really turns out to be, now I'm showing you only the absolute value. So it's really a 2-dimensional Gauss function. And this is a deformation of it. Of course, we have seen the frame operator is not invertible, even if you rescale it properly or so. So this is what you can see. And maybe just to come to an end with this Garber stuff for today is to indicate to you that we can do the same thing with an irregular family. So how can we generate an irregular Garber family? You're giving me a collection of positions in phase space. And here I'm just taking a random matrix with, and I would have 3 per mil probability. Otherwise I'm getting too many points. And you see here already, I'm getting 623 points. That's okay. And then, so here the spice command has worked properly. I'm doing an axis plot and with a title. So this is how I'm producing such a plot. And then I'm having a different command. You have seen the gabbasp with product domain, where I just put lattice constants A and B. And now it's just a 0, 1 function. We have different other formats. I could give you the sequence of coordinates in the running MATLAB way or so. But here is now a 0, 1 matrix. And because it has 623 entries in my example, I will get a collection of 623 row vectors. Now, you have seen the condition number of the Garber family is quite decent. I'm not sure if this is the same as we had before, but the irregular one, it's already in the order of 6,000. So this is, of course, because it's not so nicely spread. Now, of course, you can try to understand well those Garber families and ask, when is it a good family or not a good family or so? This was a random experiment, so I cannot just tell you my intuition or experiences, what I can say about this set. I would say, well, there are some clusters. There are like 5 or almost 7 points very close to each other, and some other clusters, almost 4 here or so. And there are some big gaps. So it's rather inhomogeneous. And that's why the condition number is not so good. There are other ideas to take maybe a lattice and move every point a little bit 2, 3 pixels to the left and to the right. And then you will see it's not perfect. It's a bit deteriorating, but it's still a very good system. Now, what we have seen here, maybe I'm concluding with this. If you have a regular Garber system, so with AB in this case, or more generally, it will be a lattice, then the dual system is again a Garber system. So if I show you the window, the spectrogram of the dual window, you know how the whole family looks like. You just have to move these pictures to all the other points. Now, here I'm demonstrating the property that happens when you have now this dual system. And I was just showing you the most important ones, so or a few of them or so. And you see these dual things are not so nicely concentrated. And I would say the theory tells us, roughly speaking, if your system is dense enough, so if I would not have these big gaps, and these big gaps create this bad condition number and this dislocation of the dual atom, then I would have still very good localization. So only recently I did an experiment for Arvin, more or less, showing that if you're taking kind of random Gaussians, which are a little bit rotated in phase space, you can find dual families, but they all are centered at the same place. So here, because it's really, well, it's still a frame and it's still good, but I wouldn't like to use this frame because it's really was necessary to invert this big family or so. And yeah, this is an attempt to say how badly localized these things are. So I'm saying I'm taking now the short time Fourier transform of all these guys. So I'm not just plotting an individual one, but you see already here, this is showing up at one number, another dual element is here. We don't know quickly which one of those 623 points are relevant. And if you accumulate this, you find out, and that's kind of the summary or so of this observation, that many kind of side lobes, maybe even significant amplitudes appear in those areas which are so small. So if you would add up the spectrograms, they would give the right spectrogram of your signal X, but you would need huge coefficients and you would have highly oscillatory terms. So it would be interesting, of course, to say, well, if we do now the synthesis, can we reconstruct? And you would say, yes, the reconstruction is not so bad. But then you can say, well, how are the partial sums? Are only the neighbors contributing to this thing? And then you would see that there are so many kind of people who have, I mean, it's like the fire that we did recently. Assume there is a fire, then of course the fire guard from these villages will come to help. But if it's a really big fire, then from a very big area, people have to come to support. That's kind of my intuition, that the dual windows, if everything is under control locally, it's fine. But if there is a big problem due to a big hole in the set, then very far, relatively far distant elements have to contribute, which gives this bad delocalization. And I'm quite sure we could look at the Garber frame matrix of such an operator and would be bad, but we will discuss this in a way. And just one way, it's an experiment at the moment. Most of the time I'm saying, well, how can you determine the density of a point set? And the answer is, I call it the Gaussian density. I would convolve this indicator function with a two-dimensional Gauss function. So I put a little Gauss function for each of those red dots, and then I would look at this, how the convolution is done with a two-dimensional Fourier transform. All this is not relevant or so. And you will see that the density is high in this area where you have a lot of points. So that's creating these blobs or so. And one might have some intuition of what's going on with the frame operator, but I think that's beyond this, far beyond the scope of what we're doing right now. And that's why I'm finishing now with this part of the section, and we are at the end of our time.